Hello, so in this lecture we are going to discuss about the Maxwell's tensor and the momentum density associated with it. So recall that the electromagnetic force for a charge Q is given by, moving with velocity V, is given by QE plus V cross B. Now, what is Q? Q is rho times dV. So this is rho. Let me write this as this. So this is rho E plus rho V cross B. And then we have the volume integration. Or in other hand, this is, and well, so this is, what is the rho V? Rho V is J by C. So therefore we could write this as rho and then E plus 1 over C and then J cross B. So where this whole thing 1 over J by C is essentially rho B. And then we will be doing the volume integration. Now let's use the Maxwell's equations. Now since Maxwell's equations gives, let's see what they give. They give the value of rho as, so once again I will be talking about the free field only. So therefore this is going to be, so now since Maxwell's equations for epsilon is equal to 1 is equal to mu gives, we will have del dot E is equal to 4 pi by rho. So therefore rho is going to be del dot E by 4 pi. And similarly over here, what we have del cross B minus 1 over C del E by del T, that is 4 pi by Cj. So we will have 1 over 4 pi here as well, because we are talking about, so this is going to be J by C. So let's put these values to the equation number 1. So this is 2.1, this is 2.2. So 2.1 and 2.2 in 1 gives, what it gives is the following. We will have the electromagnetic force should be equal to rho, which is 1 over 4 pi. Let me write it over here. Integration. This is gradient of E and then the E vector plus J cross B. J by C is 1 over 4 pi, which is out, cross B. So this is del cross B, curl of B, and then cross B minus, we have 1 over C del E by del T, minus 1 over C del E by del T. So this is going to be equal to minus 1 over C del E by del T cross B. So this is all we will get. Now I will just put the value of, so here we have del dot E. So let's try to write an analogous term for this, which is going to be 1 over 4 pi. So here we have del E by del T, E cross B. There should have been an analogous term with del B by del T cross E. So let me first try to write. So let's suppose we have that, then we could write this as minus 1 over C del of del T of E cross B. And then what would have been the difference? Well, in fact, this should be 1 over 4 pi C. The integration, of course, dV. And had it been like this, the difference would have been plus. So we have had 1 over 4 pi is common, and then we will have 1 over C del T of B cross, I'm sorry, this should be del E by del T. So del T, so E cross, so this would have been E cross del B by del T. And then plus what we have over here, del dot E. So in the similar manner, we could also write, okay, in fact, let me just combine these things. So this is gradient of E plus, in a similar manner, we would have written this as fill. So why it is okay? Because this is anyway 0. So I could just write 0 times B, which is 0. Now the third term is curl of B cross B. If we just shuffle it, we could write this as B cross curl B. So we will have a minus sign B cross del cross B. Now let's see what is left. Well, this is already absorbed. That's it. So then this whole thing should be integrated with respect to volume. Now what I could do, I could take this term outside on the other side. So this is going to be F electromagnetic plus 1 over 4 pi C del T of E cross B dV. In fact, what I will write so that this makes more sense to us immediately by looking at. Okay, so this is going to be now del B by del T. Del B by del T is minus del cross E. So that's very good. So this is E cross del cross E. So let me write the E dependent terms first then. So this is going to be 1 over 4 pi. It's going to be del dot E, then E minus, in fact, let me, okay, so this is minus E cross del cross E, and similarly we have another term plus what we have del dot B, then B minus B cross del cross B, and then this whole thing should have a volume integration on it. So now what we see, we have got duplicated terms for E and B. So let me try to replace this whole thing by something interesting. So this is basically written as, this is written as sort of del dot T. Okay, so this is basically del dot T and dV. So this is defining. So this I could write as minus of del dot some tensor. So basically this is y vector del dot T and dV. Or this could also, using the Gauss's theorem, could also be written as minus of, I'm sorry, T by vector dot n hat d. Or what we will get, F electromagnetic plus del t of, then this is what? F is basically dp by dt, and that should be actually minus dp by dt. So this is some sort of minus g by dt. Okay, and because you have over here E cross B, so this should be sort of G matter. Okay, so this should be G matter, and that should be equal to sort of minus, in fact plus del of del t, and that should have been del t, I'm sorry, this should be minus t dot, well this is y vector, please remember this whole thing. Okay, so this is the equation we would have got. This is the equation number 3 with, what is my G matter? G matter is 1 over 4 pi C cross B. Okay, so this is one thing, and then we have Ty vector. This is also written as Tij, and that would be basically 1 over 4 pi, and then we could write this as Ei. So remember we had E dot del E, and del is gone, so this is E dot, so this is Ei Ej plus Bi Bj, so this is from the curl term, and then the gradient terms, divergence terms will give you E square plus B square and delta Ij. So that's how it's going to be look like. So this is called the stress tensor. Why it's called stress tensor? Because its diagonal elements represents the normal forces, and so these are the normal forces, and these off diagonal elements represent shear forces. So therefore this is also called the stress tensor or the Maxwell's stress tensor. Okay, so from here what we had found is the following. I'm sorry, this is G field. So G field is the momentum density of the field. Okay, so G field is the momentum density of EM field. Now del dot T, that should also be represented like some sorts of density. What that density should be? That should be divergence of T, that should also be. So this EM is what? EM is, if electromagnetic, is due to some particle, and that particle should have some mass and sorts of those things. So if EM could also be written as minus of dgm by dt, this will be matter, and of course we will have the dv. So this is G matter is the matter momentum density. So if we plug these equations in, so using these, what we could write is the following: dg by dt, okay, or rather minus del dot t, that's my right hand side. So this is again the y vector plus dg field by dt, that should be equal to F electromagnetic, which is minus del G matter by del T. Now you might ask why I had written minus del G matter. Because I want to write everything along a given direction, that's the outward direction. Okay, so this relation, okay, so let me try to give you the equation that we had derived in the previous lecture. So this resembles del dot S plus del, we have energy density, and that was equal to minus E dot J with, well, E was my energy was 1 over 8 pi E square by V square mu. That was my definition for the energy density. G matter, G field is C by 4 pi E cross H. That E cross 1 over 4 pi C E cross B. Okay. So this you could check is essentially nothing but S by C square, with S was defined as C by 4 pi E cross H. So these were all the definitions. So now if someone asks what would be the torque, so the torque is going to be simply tau is going to be R cross F. Okay, so this will give us the value of torque, and also R cross P. What is this quantity called? It's called the angular momentum. So that's going to be R cross S by C square, R cross G. Okay, so with these things we end. However, just before ending, we would write the stress tensor, the forms of stress tensor, by taking the propagation of electric field alignment along different directions. So assuming E to be aligned along the third direction, so Z direction, what would be the electric components of the stress tensor? So they would be written as just the diagonal terms. So we will have minus 1 over 8 pi E square minus 1 over 8 pi E square, and rest is going to be 0. Okay, let me write them all properly so that there is no confusion. And similarly, if P, okay, I'm sorry, there should be a negative sign in these things because the alignment is along positive direction. So it should be plus along the third direction. Similarly, for B along Z direction, you could check that Tm is going to be B square by 8 pi, once again a minus sign, and a plus sign over here. The rest are going to be 0. So now clearly the stress tensor and the pointing vector are all making sense. The stress is essentially caused along the direction of motion as well as the other directions as well, if there are some off diagonal components present into the stress tensor. Okay, so this completes at least the review part of the Maxwell's equation. The actual things would start from the next term onwards. Now, some of you were asking what book I am following. So this is the Introduction to Electromagnetic Theory. And this is by J.B. Marion and Hilt. I don't know what the first thing is. Okay? So we will in fact be following this book for both units 3 and 4, except for the last topic, optical fiber, and the book for that would be informed when we will be discussing that particular topic. Thanks a lot. Stay safe and keep learning. Thanks.